Hi all. In this video, we'll be taking a look at vectors. In section 6.6, it has a lot of detailed information on vectors and a bunch of different types of problems. Each type of problem, though, I think you'll agree once you get used to them, it's really not that bad. And it introduces a fun, new, and very useful concepts. So the objectives in this section, the first thing that we'll be doing is using the magnitude and direction to show vectors are equal. So a vector is just something that has a magnitude and direction, and if they're both equal, then the two vectors are equal. We're going to visualize scalar multiplication, vector addition, vector subtraction, and geometric vectors. Represent vectors in the rectangular coordinate system. It's done pretty easily. Perform operations with vectors in terms of I and j. I is going to be the horizontal displacement. J is going to be the vertical displacement. And then find the unit vector in the direction of v. And then we will write a vector in terms of its magnitude and direction. That's important. And then lastly, most important is to be able to solve applied problems involving vectors. Okay, so first up, a vector. Quantities that involve both magnitude and direction are called vector quantities, or typically we just call them vectors for short. So if I say something about there is a 30-mile-per-hour wind blowing in a direction of 15 degrees east of north. Then you can say, wow, okay, he's given me a direction. He's given me the magnitude, the speed of the wind. That is a vector. Now, if I just give a quantity, but I don't mention a direction, well, that's just going to be a scalar. We can say a scalar quantities or scalars. So a scalar has a magnitude, but no specific direction. Now, if we do directed line segments and geometric vectors, then we can say any line segment can represent a vector. This is the vector PQ, where clearly this vector is taking the initial point P to the terminal point Q. So you can say, well, the magnitude of this would just be given by whatever the length of that line is. And of course, the direction, you could put an XY axis right here and say, well, this looks like maybe about a 60-degree angle or something like that. We could also give the direction by the slope. If we had an XY plane and we knew what the X and Y values were, we could say, well, all right, its direction could be given by its slope of how many Y values it has to increase for the number of X values that it increases. Now, also important on this page, whenever we denote the magnitude, it looks like a double absolute value sign. Then the magnitude is just going to equal the length of the segment taking P to Q in this case. Now, just as far as notations, anytime you see in your book or on my lab, the vector notation, it'll always look like a bold B or a bold W, whatever letter is representing the vector in the case, it'll always be emboldened. If you're writing this out on paper, you're really supposed to put an arrow over the V or the W to represent that it's a vector. As I was working the homework, there's so many V's and W's and U's and stuff. I kind of stopped that. It's proper notation to do that, but you don't have to. I will know that if you're using V, W, and U in a section about vectors, that, yeah, it's representing the vector in the problem. But technically, you should put the arrow over there. And the same thing, if you're trying to do the magnitude, we'd say, well, the magnitude of vector V or vector W, you just put looks like the double absolute value sign around it. That's going to represent the length of the vector graphically. Now, application-wise, it could represent the weight or the speed of an object. So if an object is going 600 miles per hour at a specific direction, well, that speed is going to represent the magnitude of the vector. Representing the magnitude of the vector on paper, you just put an arrow over the indicators for the vector and then the double absolute value sign. Again, though, that arrow's not mandatory, but it's formal notation if you're writing it out by hand. Now, when we try to determine equal vectors must have the same magnitude and the same direction. Now, if I'm looking at these two, I can say, well, vector v is equal to vector w, even though they're not in the same place, but they're equal vectors because they're going to have the same magnitude, they're the same length, and clearly they're parallel, so they're going in the same direction. So I can say vector v would equal vector w. Now, on the other hand, vector v would not equal vector w in my part B, because again, I tried to draw them out with the same length, but w is not going in the same direction of v. It has a lower slope than the slope of v, so those would not be the same vector. If I ask about part C here, you can say at first you might think, hey, yeah, they're going to be parallel, and it looks like they're the same length. Both of those are true, but the direction is opposite. Notice V, its starting point. I did the red point as the starting point. Its starting point is here, and it's moving down. Well, vector W is going in the opposite direction at that exact same rate, starting down and going up. So actually here, W would be the negative of V. But here I'm just concerned about, hey, are the two vectors equal to one another? No, W would equal the negative of V. Now, in this case, these two vectors have the exact same direction, but clearly they don't have the same magnitude. Vector V looks like it's about half the length of vector W. So you know, hey, V does not equal W in this scenario. Now, if I want to be able to find the magnitude of vectors, if I'm given points, there's about 3 or 4 homework problems like this. All you have to do is say, well, if I'm given the beginning point and the end point, then I know how much this vector u is moving this object horizontally, and I know how much it's moving it vertically. I could say the magnitude is going to be the square root. It's the length of that line segment between the beginning point and the ending point. I can say, well, the length of that line segment, you could just do with your distance formula. The magnitude or the distance is equal to the square root of the change in x quantity squared. So you'd say, well, -2 minus a -5. And then you'd say, oh, that's, I accidentally put the change in the x and the change in y's, but that's okay. It's still going to be correct. So it'd be -2 minus a -5 quantity squared. And then your change in y's would be 6 minus 2 quantity squared. As long as those two are both in there, it's fine. You can say, well, the change in the y components is 4. We'd square that out. Change in the x components, -2 plus 5, it's going to give me it's changing 3 units. And you could say, well, all right, then it's 4 squared plus 3 squared, which gives me the square root of 25. I know that vector u has a magnitude of 5. Now, if I look at vector v over here to determine if it's the same, I can already just eyeball it and say, well, it looks like it's the same length in the same direction. I'm thinking this is the same. To verify it, I went in and I did the magnitude. I said, well, the magnitude is going to be the change in x's quantity squared plus the change in y's quantity squared. We could say the change in x's are going to be 5 minus 2 quantity squared plus the change in y's 6 minus 2 quantity squared. Again, we get our square root of 4 squared plus 3 squared. We're going to get a magnitude of 5. So now I can see that their magnitudes are the same. I could further look at it and say, well, what about their slopes? This one is rising up 4 units as it runs 3 units. Well, this one is rising up 4 units as it runs 3 units. They both have the same slope of 4/3. So they have the same direction because their slope is the same. They have the same magnitudes. So we can say these two are equal vectors. We can say vector u is equal to vector v. Now, again, that does not mean that they're in the exact same place in the plane. It just means that this vector will do the same thing to this initial point, to the terminal point, vector u or vector v. It's irrelevant. Both of these vectors are going to take an object, move it 3 units to the right, and then move it up 4 units. That's what's the important point about the vectors, what's happening from the beginning to the ending. Now, scalar multiplication is when we take a vector and multiply it by some constant. We'll call it the scalar multiplication k, so some constant k. Anytime you multiply a vector by any number except for 1, it's going to change the magnitude of the vector, but it's not going to change its direction. Now, I will say with the caveat that if you multiply by a negative, it turns the direction in reverse, of course. So it still has the same pathway, it's just the opposite direction. So I could say, all right, let's assume that here's my standard vector v. Then I say, well, let's multiply vector v by a scalar multiple of 2. Well, it just doubles its length. So you say, if this is my starting point and this is my ending point, now it's going to go from that starting point to that ending point in the exact same direction, but go twice the length. What if I say 1/2 v? Well, it'd be half the length from the beginning to the ending point. Now, what I was talking about down here, if I multiply by a negative, it's going to have that same direction, but now you go from that starting point, which would be right here, and instead of going up, you'd be going down because you multiplied by a negative scalar. It's reversing the direction of the vector. Now, whenever you multiply by a scalar, you can put that k value inside your magnitude formula, or you could just simply say, if I know the magnitude of vector v, then the magnitude of k times v is just going to be k times the magnitude. Now, I should have said the absolute value of k times the magnitude, because when we talk about a magnitude of a vector, we talk about its length, and we would never say a vector has a negative length. So it wouldn't make sense to say, hey, is the magnitude -5? No, the magnitude is 5 or any positive number. And you can see in your magnitude formula, the magnitude is equal to the square root of the horizontal component squared plus the vertical component squared. We know we can only get positive values outside of the square root. So whenever we multiply by any magnitude, even if it is changing the direction, you're going to multiply by the absolute value to find the new magnitude. Now, the vector kv has a direction. We can say it's the same direction if k is greater than 0. Of course, it's the opposite direction if k is less than 0, but it's still going to have the same magnitude of whatever the kv would be. Now, what if we are wanting to sum vectors together? Now, we've already seen a few vectors plotted out, but let's say in a case like this, I ask you to plot vector u, and you said, well, this vector u has a much more of a horizontal change than vertical change. It's just moving up gradually as the horizontal changes. Well, if I could plot out vector u, and we will be plotting these in just a moment, so don't worry about, well, how do I plot it out? We'll be doing that. But if I wanted to plot out the resultant vector of u plus v, all I would have to do graphically is plot out u. And then at the end of my vector that's representing u, I would plot the vector v. So the beginning point of v would be on the terminal point of u. And then whatever vector v tells me to do, and it looks like vector v tells me to move up a little bit more than I'm moving to the right, then I can say the resultant vector u plus v is going to be the result of starting at this initial point, which is at the beginning of u, going all the way to our ending point at the end of v. And that's the result of the action of vectors u and v. Now, what if I wanted to say, well, what about u minus v? Or in this case, v minus u? Well, I'd say, well, all right, no big deal. Let's assume that vector u is a positive, this would be a positive horizontal vector here. Vector v has a positive horizontal and vertical component. And I'm wanting to say I want vector v minus vector u. Well, v minus u is the same thing as v plus a negative u. So I know if positive u is telling me to go horizontal this distance, the negative u would tell me to go horizontal in the opposite direction. So then if I plot out u minus v or v minus u or v plus a negative u, I would just say, well, plot out v. And then at the end of vector v, subtract u from it. And then I could say, well, all right, this is v, and then this is the opposite of u. The end of that vector u after I subtract is going to be the end of the resultant vector v minus u. I would say this blue vector is my resultant vector v minus u. Resultant vector is any vector that is a result of two or more individual vectors. And that result could be addition, subtraction, multiplication, division. You could do a whole bunch of things with these vectors. Right now, we're looking at vector addition and vector subtraction. Now, let's bring in another vocabulary term, unit vectors. This allows us to work with vectors more easily. Like in the last problem, I said, well, vector u, that's just a positive horizontal vector. It looks like it's moving to the right a certain number of units. Well, I guarantee you that in the last problem, vector u only has an I component when it's written out in terms of I and j. The unit vectors, I is one vector force to the right. J means the unit vector one unit up. So if I say, well, what if I let vector v equal I plus j? I mean, one to the right, one up. The vector v would look like that right there. It'd be a diagonal line from 0 up to the ordered pair 1, 1. It would have angle theta of 45 degrees because it would be splitting quadrant 1. Now, whenever we're representing vectors with these rectangular coordinates, we can say, well, then any vector from 0, 0 to any other point in the plane, A, B, can be represented by the vector v is equal to the coefficient of I is A, the coefficient of j is B. Please again remember, I is going to represent the horizontal change, j is going to represent the vertical change. Since I is the unit vector in the horizontal direction, then any change of number of units in that direction is going to be the coefficient of I. Since j is the unit vector in the vertical direction, any change in the y values would be the coefficient of j. So you could quickly and easily see where this ai plus bj comes from. You say, well, the x component starting at 0 going to a, so the change in x is a minus 0. A is your coefficient of I. The change in y from 0 to b minus 0. It's changed b units, whatever b is equal to in this problem. That's why b is the coefficient of j. Now, I know that if I were to draw this out and I'm making the assumption that a is a positive value and that b is a positive value, I could say vector v, which would equal ai plus bj, it's going to have a magnitude. You can say, well, clearly if the horizontal factor here is the a value, the vertical factor is the b value, then the diagonal, which is going to give me the magnitude of the vector, is just going to be the square root of the horizontal factor squared plus the vertical factor squared. That's where we're getting the magnitude of v is the square root of a squared plus b squared. This carries over very nicely back when we were talking about polar coordinates, where we said the distance from the pole to the point in the plane was just r is equal to the square root of a squared plus b squared. Same idea here. Now, for my next example here, I want to sketch a vector 3i minus 3j and find its magnitude. Easy. You say, well, this is telling me it's moving 3 to the right and 3 down. Absolutely. 3 to the right and 3 down. Here's my point. So then I'd say, well, 3 to the right, 3 down. Here's my vector. So the vector always starts at the origin. That's your initial point. whenever you're plotting these out. And then it's going to go to the ordered pair 3, -3, since this vector specifically says it's going to push anything to the right 3 and down 3. That's what this is saying. So if you're starting at 0, 0, your ending point is going to be at 3, -3. Now, I could then find its magnitude and say, well, the magnitude is going to be the horizontal change squared plus the vertical change squared. That's going to be the square root of 3 squared plus -3 squared. That's where this came from. And then you say, well, all right, both of those, when we square them, are going to give us 9. 9 plus 9 is 18, which I could then factor back and say, well, that's 2 times this, the square root of 9 times 2, and the square root of 9 comes out as a 3, and I get 3 on the root of 2. I would like you to reduce down your roots whenever possible. Now, let's look at a problem in which we're representing a vector with rectangular coordinates. So unlike the last problem where I went ahead and gave you your vector in terms of I and j and asked for the magnitude, this time I just want to give you the initial and ending point. So I say, well, you have a vector that's starting at the ordered pair -1, 3. It's ending at the ordered pair 2, 7. All right. So then I know that the vector in terms of I and j, you say, well, the I, it's just the horizontal change. So this is going from -1 to 2. The x component is increasing 3 units. You can see that here. I said, well, 2 minus a -1 shows me I'm going to have a coefficient of 3 in front of the I. What about the y component? Well, it's starting at 3, it's ending at 7. Clearly, it's increasing 4 units. I'm going to have a 4j for the vertical component here. So this vector v is equal to 3 times I. It's 3 times the unit vector in the horizontal direction plus 4 times the unit vector in the vertical direction. So it's going to push to the right with a force of 3, push up with a force of 4. And then we can say, okay, no problem. Pretty straightforward. Now, I didn't go in and find the magnitude of that last one, but we could have. We could have just said the magnitude of vector v, again, would be the square root of 3 squared plus 4 squared, which would give you 5. Now, if we're adding and subtracting vectors, a breeze. All of your operations of addition, subtraction, multiplication, division hold when we talk about vectors. So if I'm saying I want you to add vector v to vector w, then you would just say, well, all right, v plus w, you add their individual components. 7i plus 4i is going to be 11i. 3j plus a -5j is going to be -2j. The resultant vector of the vector v plus w is 11i minus 2j. What if I say vector v minus vector w? You're just going to subtract then. You say, well, take the components of vector v, subtract the like components in vector w. 7i minus 4i, it's giving me 3i. You'll have 3j minus the -5j, which is going to give you 8j down there. So you can see these pretty straightforward as far as the addition and subtraction. What if I have a scalar multiplication and I have vector v is equal to 7i plus 10j, and I say, well, I want 8 times vector v. So anytime you have a scalar multiple k times any vector, you're just going to multiply it by each of the individual components, both the vertical and the horizontal, of course. So 8 times vector v, it's just going to be 7 times 8, which is 56i. And then you'll have 8 times 10 for 80j. 8v is going to be the vector 56i plus 80j. What about -5 times vector v? You just multiply each of the components by -5, and you'd get 7 times -5 is -35i. -5 times a 10j is going to be -50j. So very, very, very easy as far as scalar multiplication. Now, the 0 vector, it just means that it's a vector that doesn't affect anything. Whether you add it, subtract it, whatever, it's not going to affect. Now, shouldn't say multiply. If I multiply something by a 0 vector, it would be 0. But if you're adding or subtracting, there's no effect whatsoever because it has no horizontal component and no vertical component. So you'd say 0i plus 0j is the 0 vector, has no assigned direction whatsoever. Now, the unit vector, and this ends up being important later on in future classes. The unit vector is defined as the vector whose magnitude is 1. We already talked about I and j are unit vectors. I is the unit vector in the horizontal direction. J is the unit vector in the vertical direction. Now, if I want to talk about a unit vector of any vector v, then you'd say, well, all right, if I take any vector v and divide by that vector's magnitude, then I'm going to get a unit vector in the direction of vector v. And you say, well, okay, that needs to make sense because what if I have a vector of length 10 at an angle of 30 degrees? Well, if I go in and I take that vector and I divide by 10, well, then I've reduced the length of that vector down to 1, but it's still going in the exact same direction. So I can divide by the magnitude, and it's not changing the direction, but it will change the magnitude to be the unit vector as long as I'm dividing by the correct magnitude of vector v. Now, let's talk about that and show that within this example here. Notice I ask you to find the unit vector in the same direction as v, which is 4i minus 3j, then verify that the vector has a magnitude of 1. Okay, so first of all, if I want to find the unit vector, I find the magnitude of vector v, which is really easy. It's just the square root of 4 squared plus negative 3 squared. I would get my square root of 16 plus 9 again, square root of 25. This vector has a length of 5. Now, in order to find the unit vector in the same direction as v, you would take your vector v, divide by its magnitude, and when you divide by that magnitude, it distributes to both terms. You'll have 4/5 I minus 3/5 j. Now, just to prove that, yes, this is the unit vector going in the exact same direction, I could say, well, all right, let's find the magnitude of this vector. It'd be the square root of 4/5 squared plus a negative 3/5 squared. You would get your 16 over 25 plus 9 over 25, which obviously is 25 over 25. And then the square root of 1 would give us a 1. So this vector would have a magnitude of 1, and it's going in the exact same direction as the original vector. It's going to increase the x component 4 times every time the y component moves down 3. Same thing here. It's going to increase the x 4 every time the y moves down 3. Doesn't matter that it's 4/5 and negative 3/5, only for the magnitude, not the direction. Now, if I'm writing a vector in terms of its magnitude and direction, again, this is going to bring back polar coordinates as it should. When we talked about polar coordinates, we said, well, the x component is just r cosine theta. The y component is r sine theta. Same thing here. If I want to talk about the multiplier of the unit vector in the horizontal direction, I would just say it's going to be the magnitude times the cosine of theta. So if I took that magnitude, if you think about this right here, if I want to say, well, how would I represent that this is moving to the left a certain number of units? I could draw a triangle in here and call this my reference angle theta. And then I know that the adjacent divided by the hypotenuse, that would be my cosine of theta. So I could say, well, all right, then if I took that magnitude and multiplied by the cosine of theta, it'll enable me to see what this horizontal displacement is here. And in my picture drawn, it would be a negative one. Then if I wanted to find the vertical displacement, the b value, I would just say, well, it's whatever your magnitude is times the sine of theta. That's going to be your coefficient of j. Let's look at a problem like that. So this one's good because it brings in your typical types of applications that we have whenever we work with vectors. It says we have a jet stream that's blowing at 60 miles per hour in the direction of 45 degrees east of north. Now, I went ahead and drew that out here. I didn't label this, but this angle right here is 45 degrees. And it's blowing in that direction 45 degrees east of north. Now, the length of that vector would be represented by the speed of the jet stream, which is 60 miles per hour. So V has a length of 60. And we know that theta here, since it's 45 degrees east of north, well, this angle here is also 45. We can just say this has to split quadrant one. Well, then if I said, well, I want you to find a vector V in rectangular form in terms of I and J that represent this vector, you'd say, no problem. The horizontal component is going to be your magnitude times the cosine of theta, where theta is the angle from the initial x-axis. So you'd say, well, that's going to be 60 cosine 45. The vertical component is going to be the magnitude 60 times the sine of the angle theta, which again is 45. And that's going to be showing that that's the vertical component. We multiply that by j. And both the cosine and sine of 45 degrees are the square root of 2 over 2. So we can see our vector is going to end up being 30 on the root of 2i plus 30 on the root of 2j. So we can see that if this jet stream is blowing in this direction, the horizontal and vertical component are the exact same. It's blowing it to the right with 30 on the root of 2 miles per hour, and it's also blowing it up at this exact same rate. Now, much better application. Gorgeous problem. If we have two forces, F1 and F2, of magnitude 30 and 60 pounds respectively. So F1, 30-pound force, F2, 60-pound force. That's why I've tried to draw F2 twice the length of F1. Now, I need to find the resultant of both of their forces. It says the direction of F1 is 10 degrees east of north. I've tried to label that right here. This angle right here would be 10. And then the direction of F2 is 60 degrees east of north. So from the y-axis to this, I would have 60 degrees, which means this angle down here is 30 degrees. The angle to F1 would be 80 degrees because it'd be 90 minus 10. So 80 degrees to this force F1, 30 degrees to this force F2. Now, we're supposed to find the magnitude to the nearest hundredth of a pound and direction to the nearest tenth of a degree of the resultant force. Now, whenever you're drawing these two forces out, yes, I drew force 1 and yes, I drew force 2, both connected to the origin, and we're trying to find out what happens when both of them act on an object. Now, you could have solved this graphically by drawing force F1 and then at the end of F1 drawing force F2, to where you say, well, it's just going to be at an angle of 30 degrees from, if I drew an XY axis right there, 30 degrees with a length of 60. It'd be hard to do graphically, but you could. I kind of like the way I've drawn it here with the two forces out individually, F1 and F2, and we know the resultant force is somewhere in between the two. Now, just using some common sense, I would think that the resultant force should be more towards F2 than it is F1, because F2 is a 60-pound force and F1 is just a 30-pound force. Of course, the 60-pound force should overpower the other, but we'll need to find the resultant vector from these two vectors acting on an object. Now, I'm supposed to find the angle to the nearest degree and the magnitude. That'll just be how many pounds of force are acting on it. So first thing I have to do, I need to get the ij component form vector of both F1 and F2. So I go back and I can say, well, vector F1, that was the one acting at or having a magnitude of 30 at a direction of theta is 80 degrees because it's 10 degrees east of north. So notice how I put that in. The horizontal component, the magnitude times the cosine of theta. The vertical component, the magnitude times the sine of theta. Of course, the horizontal component you multiply by I, the vertical component you multiply by j. Now, this is just calculator, So you'd say 30 cosine of 80, I get my 5.21i. And then my 30 sine 80, I get my 29.54. So it makes sense of this 30 pounds of force, if it's acting at an angle of 10 degrees east of north, clearly more of the force is going north than it is moving to the right. That's why the x component is just barely positive, but the y component is extremely positive. Now, for vector F2, it's the one that was acting at 60 degrees east of north, so this angle theta down here is only 30 degrees. And so you'd say, well, then the horizontal component, it's going to be 60 cosine 30, and the vertical is going to be 60 sine 30. That's precisely what I did here, guys. F2 is a vector that has 60 cosine 30 I plus 60 sine 30 j. Cosine of 30 would be the square root of 3 over 2. When you multiply that by 60, you'll get 51.96. And again, that needs to make sense to you. Why is that horizontal component so large? Well, because we're moving, if it's going at an angle of 60 degrees east of north, that vector is going far more to the right than it is going up. And you can see, yep, the force to the right is going to be 51.96 pounds of force. The force upward is just 60 sine 30, which is 60 times 1/2. I get a force upward of 30. So now, if I want to find the resultant force of both of these vectors acting, then you can say, well, all right, then I'll just sum the two vectors together. I had vector F1, vector F2. I add their individual components, 5.21 plus 51.96 gives me 57.17i. When I add the j values, the vertical components, I'll get 59.54j. So this component vector, or sorry, I should say this resultant vector f, it's going slightly, or has more force slightly up than to the right, but it's going almost at a 45-degree angle. But I need to find that angle, and I can. The first thing I did here is I found the magnitude. So with what pounds of force are these two vectors acting? I know that if they were totally complementary forces, which the only way that they could be totally complementary is if they're acting in the exact same direction. If they were acting in the exact same direction, then the magnitude force would be 30 plus 60, it would be 90. We know that these aren't going in the exact same direction, so it's not going to be 90, but at least they're both pushing up, they're both pushing to the right, albeit at different rates. So there's not going to be a whole lot of canceling out. And so we'd say expect it to be close to 90, and it is. You can say, well, the magnitude of vector f is the square root of the horizontal the horizontal coefficient squared plus the vertical coefficient squared. And when I take that horizontal component squared plus the vertical component squared and take the square root of it, I get approximately 82.54. So I know the resultant vector is going to go with a pounds of force of 82.54 pounds of force. In what direction? Well, that's what I'm finding next. Just by looking at it, it looks like it's approximately a 45-degree angle if I had to guess, but I don't have to guess because our tangent formula, we say, well, we know that the tangent is going to equal the vertical divided by the horizontal. We've already been saying it's going up. This is the vertical component. This is the horizontal component. So it just makes sense to say, well, then the tangent is equal to that vertical divided by the horizontal, 59.54 over 57.17. And fortunately, since this is in quadrant 1, you know your calculator is going to give you the answer that you need here. So we can go inverse tangent of 59.54 over 57.17. We'll get our 46.16 degrees. I think I asked us to round to 1 decimal place. So on the next page, I'll change that to 46.2. But now, keep in mind, if we were in quadrant 2 or quadrant 3, that inverse tangent on your calculator is not going to give you the correct answer. but it would give you the tools to get to the correct answer. So you would know the placement that it would be in quadrant 4 and 1, and use that same placement. If it's supposed to be in quadrant 3, then you just say, well, just add 180 degrees to that. If it's supposed to be in quadrant 2 and you're getting an answer in quadrant 4, then add 180 degrees to that and you'll get the answer that you need. Now, so to summarize this application problem, we can say we know that the two forces that are acting on this single force are going to be approximately at 82.54 pounds of force, with a direction angle of approximately 46.2 degrees, since it's said to the nearest tenth of a degree. And that would be our resultant force vector F. That's a cool problem, guys. Please let me know if you have any questions in this section. I'll be glad to help in any way I can.